Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. So what is Data Unchained all about? Probably many of you subscribe and listen to the show every week, but for those of you who are new to the show, this is all about how the paradigm for data access has changed. In today's decentralized world, getting data to remote workers, distributed applications, different cloud regions, and different data centers is really a challenge. Data Unchained digs into both the challenges as well as the solutions to make data an asset as a globally accessible resource. Today we have David Flynn joining us, and he has been a guest on our show, and actually his company is the sponsor of Data Unchained. So David, thank you for joining and taking some time to talk about some of the new hype cycle around data.
It's my pleasure, Molly. Thank you for having me on.
And David, can you tell us a little bit about your history, both as a technologist and a little bit about Hammerspace?
Well, I think I'm best known for my role in founding the company Fusion.io, where we introduced high-performance enterprise solid state and the concept of putting it on the PCI Express bus. So that was the company Fusion.io.
And Hammerspace, you founded it, over 5 years ago now, I guess. What does Hammerspace do?
Yeah, Hammerspace builds the data orchestration and file system for allowing you to use data that is physically distributed across flash inside of servers like NVMe or different storage systems, or even across whole different data centers. So we have built at once a file system capable of spanning all forms of storage from all vendors and in all locations simultaneously. But that, what a lot of people refer to as a global namespace, is really a means to an end. The purpose behind it is to allow data movement to then be done behind the file system in a way that's completely transparent to the access, so that everybody can have local access to remote or distributed data.
So I know that you and the company just recently closed a funding round. Before we jump into today's topic about AI, what is it that investors are looking for in a pretty tough economy? What is it that you felt like were the reasons that they leaned in on wanting to invest in a fairly large capital round for Hammerspace?
Well, I think it's kind of twofold. Number one is, obviously, most investors are looking at it from the financial return perspective. And so a company that's growing 300% and 400% a year, and that has a very large market opportunity is, of course, foundation to most. But the investors that we're working with, for example, Kathy Wood from ARK Investments or Peer 88, even Prosperity 7, these groups are specifically looking for disruptive innovators, companies who stand to change the underlying game in a way that can transform entire industries. And in this case, how data is mapped and managed across the infrastructure will be radically changed through data orchestration. And so it's really that twofold: the financial side of things, but also the disruptive innovator capabilities to disrupt entire multi-billion-dollar industries.
So thinking of multi-billion-dollar industries, I don't know what the latest estimates are on how large the AI market is or is going to be, but it's much more than multi-billion, I think. I think there's estimates even using trillions, I've heard. What has made AI so important? Why now? Why is it that, the technology you can't pick up a business or a technology publication without reading about?
Well, on the one hand, I think it's awareness with ChatGPT, making it blatantly obvious that these systems are capable of things that we would not have imagined, right? But it's also that the technology only recently got there. So our awareness of it has followed, of course, but it's only been in the last couple of years that these things have been capable. Large language models in particular, because we humans are, definitely work in the realm of language, and to see that, rivaled by what you can do with these LLMs is just really opening people's eyes.
And you said that some of the technology has been developing. Is it the software that a large language model runs? Is it the hardware, the processing power, like the GPUs? What is it that has evolved over the past few years that's made it possible?
Actually, I would say that less the hardware initially. There were certain things that in the past decade folks realized needed to be done differently in neural networks, and it made all the difference on that. And now, of course, that we're seeing what they're capable of, it's a race to throw ever more hardware at it. So it really was innovations in the software over the past just 10 years, I would say, that really lit the fire, because it solved key challenges with neural network and training. And now we can push the envelope, and hardware performance can make the difference. So people are now trying to scale that up as fast as they can.
That makes sense.
So first it was software, now it's more hardware, now that we have the software recipe.
And as you think about the data pipelines, of course, all of this is being fed and fueled by, you put data in, you get interesting information out. Mm-hmm. What do the data pipelines for these AI models look like?
Well, I think in a sense they look more like the more exotic HPC or supercomputing pipelines. Very large numbers of machines running in parallel, with jobs that have to work in lockstep. So if you have any component failures, you need to have made a checkpoint so you can roll back and start at the last checkpoint. These are things that are classic in the HPC world, and now we're seeing that needed in the AI and language training. But it goes beyond just the parallels to the supercomputing world, where parallelism, no pun intended, is super important. But also to what it means about the data sets, with now the all data, not just the structured data, not just the stuff that is so painstakingly curated into specific columns and rows of a relational database, or even a NoSQL database. I mean, this is kind of if we go from SQL databases and stuff to NoSQL databases to vector databases and then AI ML stuff. That's sort of a progression that we've been on. But what it means is that the data no longer needs to have been pre-structured, and it also means that data's lifetime is no longer just from hot to cold. We don't have, things that go from being useful to then being useless and being put into archive or active archive, or maybe you'll look at it. Now you need to have collected the whole thing and have the whole thing able to be fed in. So it really affects and creates a nonlinear data lifecycle, and it means it's the bulk data now that matters, the source material, the unstructured data. You want to go all the way to the source.
So when you talk about that, I think that's really interesting in a world where tiering data and lifecycle management of data has been a standard. What does that look like in an AI pipeline? Is it a whole bunch of systems where all this data now needs to be kept hot, and so it's sitting in really expensive, high-performance NVMe storage? Or is it done through metadata? How do you make all of that data accessible to the AI engine?
Well, there's different data at different stages. There's the input material, the source material that you're feeding in, and that has to be done. Basically, you need to feed potentially hundreds of machines with GPUs with the same data set. And if it's a multimodal model, one that includes video, audio, imagery, then it's going to be very large amounts of that data that needs to be sent in duplicate to every single one of those machines. And then, so that's a read-intensive workflow. And then you have, and it's very bursty. It's when you need to feed the stuff in. And then you have the opposite, which is needing to make checkpoints periodically, which is the epitome of bursty and in the opposite direction with writes coming out of the system. And then, of course, the researchers, and in their work, they need to have scratchpad at a petabyte scale scratch pads for moving and munging around these input material, the resulting output material, using the thing that's trained to do more curation of the data set. And so you really kind of have that third piece, which is the human interaction, where these large data sets going in and coming out are all coordinated. And the background to all of this is having a file system. And it's kind of amazing that we're going back to the future here of the convenience of a file system, that the OS needs to understand it. You need to be able to maneuver around it, copy files around. For a long time, as an industry, we had been moving towards using REST interfaces to object storage and rewriting applications to do that. But that was solely to try to get to cloud scalability. But it meant abandoning all of the conveniences of a real file system with the data services and the fact that, you can actually put your binaries and executables on it and actually run programs from it. You can't do that in an object store. So we're now seeing that there is a resurgence for a desire to have real file systems, but big amounts of data and shared across the whole data center. And this whole thing about, you need to rewrite your application to use object storage. It's like that. All that's going to do is slow down how fast your researchers can build, these AI models and bring them to bear on specific business problems if you're still worrying about rewriting your application. So it's kind of amazing that we're seeing even the huge hyperscale companies at hyperscale who had, been very early on board with doing REST interface, user space, things to object storage, now needing to have a true shared file system. And it's interesting that in the high-end supercomputing world, the HPC world, they never left that. And they, the need for large parallel, but a true file system was needed. We're seeing that is a massive change.
Can you give us an example of the performance requirements, maybe some hard numbers? Is Hammerspace running in some of these AI environments today, or is it kind of theoretical?
Yeah, we have the privilege of working with some of the companies that are at the forefront of doing this at scale, some large language models that you would know about, and doing it with tens of thousands of GPUs across many thousands of servers. And what we're talking about here really does rival the most high-end in the supercomputing world. I was talking with somebody in the U.S. Department of Energy about the scale of the I/O subsystems for their supercomputers, and it's on the order of 80 terabits per second, doing 10 terabytes per second kind of numbers to be able to do checkpoints and stuff on those systems. And we're doing that scale of work today in hyperscale data center with thousands of nodes, each attached to 100 gigabit, 200 gigabit Ethernet, feeding things at 20, 30 terabits per second kind of numbers. Now, this is not everybody's going to be at that radical a scale, but it does, scale all the way down to where, okay, you have a handful of GPU outfitted server nodes, and you need to feed those. So now you need a handful of NVMe outfitted storage nodes and some way to create that as a high performance, I would say, parallel file system. So it's not your traditional NAS. It's not something that scale up or scale out NAS is going to be able to do. In the supercomputing world, we left traditional NFS and scale up and scale out a long time ago. What you need is a parallel file system. But the problem is those parallel file systems have always been exotic things where you need, custom clients. They don't come out of box, and they're difficult to administer. It's not NFS. You've probably heard the saying before, it's not Ethernet, right? And and in the in the AI world, there is a resurgence of InfiniBand, for example. But now InfiniBand is largely converged with Ethernet. You get a lot of the conveniences from both, so there's not that big of a difference, and it's all the same hardware. It's just how you want to run it, right? So, in a way, Ethernet has won because it's subsumed and absorbed InfiniBand capabilities. Well, we're seeing the same thing with, it's not NFS. The exotic high-performance parallel file systems of the supercomputing world, those are all well and good, but what you really need is something that is standards-based, that is NFS, that comes out of the box, and it's built into Linux, but is now truly parallel, like a parallel file system. And that's what Hammerspace has uniquely driven in the industry, is taking what was an academic toy, the parallel NFS, and make it into a truly enterprise NAS capable, but in box inside of NFS. And where, by the way, it's not just that the client's in box, but the actual storage nodes are just Linux themselves too. And so that's one of the reasons why Hammerspace has been adopted by some of these folks in the AI arms race, shall we say, in their hyperscale data centers, is they can run Linux on the storage nodes unmodified, and they can run Linux on their clients unmodified, and using Hammerspace as the metadata service and data orchestrator, bring all of that together in one massive parallel file system. And that is extremely attractive, that the storage node and the client all come out of the box in Linux, and that they didn't even realize they were already running the building blocks for it in their data center, that they didn't have anything really that they needed to do other than use Hammerspace as the control plane and the metadata service to bring it together.
Having come from the HPC space for a lot of my career, I think in a lot of the companies I've worked for, we were always trying to make that jump from, and representing technologies like Lustre and IBM's GPFS, that we wanted to move to the enterprise, but it was tough because enterprise adoption of a parallel file system and something that no one's seen or trained on is tough.
Yeah, it was never going to be NAS. It was never going to be NAS because it was never NFS. Yeah.
So moving to the capabilities, but doing it in servers and machines with protocols that systems and applications and administrators are accustomed to, that makes a ton of sense. I think that talking about data orchestration a bit will be an interesting conversation kind of following on this. So first, as we think about a standard-based hardware, standard-based Linux servers, is data orchestration somehow helping customers take full advantage of their hardware? What is it doing that is really helping just in a single site environment without even thinking about data that's maybe sitting in other sites?
Well, yeah, and that's the interesting thing, is we're talking here about AI and ML workloads, which are very much, they parallel the high-performance computing world of needing parallelism. But more broadly, data orchestration is needed for all forms of workflows that happen to be, any kind of data intensive, where you need to move large data sets across different regions, maybe of different clouds, or across different data centers, maybe to support having knowledge professionals working in different regions around the world. So data orchestration is absolutely the missing piece to being able to achieve that infrastructure agnostic, operate anywhere, the whole utility computing model that cloud would seem to represent, but the cloud has really been more about monolithic and being a big mainframe, right? Pick which one of the mainframe vendors you want to go to, put your stuff there, and that's where you're running. But with data orchestration, now you can pick the venue where you want to do the computing, and you can pick the venue where you want to have your knowledge professionals be able to interact in real time with the data. And you can pick the venue where you want to have the data stored long term for retention purposes. And those all three don't have to be the same place, and they don't have to be the same place at different points in time. And that's why data orchestration is so key, is because you have to be able to pick where you do the computing, where you do the interactive with the people, where you do the long-term retention, and then how that evolves at different points in time with data originating in different places and being needed in different places.
So that sounds to me like you're challenging some of the long-held industry norms of you have to move your data to your compute. Am I hearing it right that you're thinking about?
Yeah, well, that's the first thing that has to go. And the reason for that is that, especially with AI and ML workloads, the compute is not interchangeable. You've got to have a GPU farm somewhere, and it's hard to keep it fully utilized for just one organization. So it needs to be a shared resource. It needs to be a cloud-like resource. And if it's going to be a shared resource, then how do you get your data to it? You still want to maintain possession and control of your data, but while using this infrastructure. And the reason why this has been such a challenge before is that data is a platform layer construct, a higher abstraction layer construct, and infrastructure, the storage, is a lower layer thing. And yet, because the storage has owned the data presentation layer, the file system, the storage has been the provider of the data presentation layer, what that means is that data has been subordinate to infrastructure. You're inverting platform into infrastructure. And that leaves you captive. It leaves you bound to specific points in infrastructure. And that's why the whole mantra of move the compute to your data is you're going to have to do the computing on the infrastructure where the data is, because that data is a prisoner to that specific piece of infrastructure. Well, as the irony here is that there's nothing more digital than data. It's the very definition of it. It's the thing that ought to be easy to move around, right? Servers, on the other hand, especially with GPUs and all that, they have to be racked and stacked. You have to plug them into the power grid. And they are very much bound to the physical world because they need to be fed by energy to run the things. And so data is the thing that ought to move. And the compute ought to be located where it's most efficient to run that, to where you can run it as a shared resource. And in the past, it's been, that just means your SOL. You need to pick which of the big mainframes you want to put your stuff on, and then that's where it is. And it's just not going to work with these AI workflows. Too much benefit and need to be able to shop your venue and run things anywhere and have your people be interactive with the large data sets nearby in their ways. So all of this is just begging for data orchestration.
Yeah, something of a best of both worlds, where move your data where you need it, where you have available compute, where you have available power, whatever it is, right, and have the same high performance, local performance that you would get out of an HPC system. So you don't have to sacrifice on one or the other.
And the key to this is a global namespace that's driven by metadata, that's easy to replicate everywhere, and have the data be able to be moved both proactively through policy and reactively in a granular fashion. Then you're not waiting to move whole data sets. You don't have to wait for it to move before you can start using it. You get continuity of access and use even while the data is still flowing under the covers. It just, right, things might need to be fetched on demand, or you set up the policy in advance to move them. That pushed by policy or pulled by demand is uniquely enabled by the fact that the data movement is happening from behind the file system, behind the data presentation layer, and without disrupting it. And so that's why this data orchestration is something so fundamentally different from data management that we're all used to. Data management you do outside the storage, copying between them, which just proliferates more data, self-defeating. But when the data movement is behind the file system, now that becomes data orchestration. It can be done granularly. It can be done based on push of policy and pull on demand, and give you continuity of that access across different locations at the same time.
So how, I think some of the storage companies who are out there talking about their capabilities in AI are certainly focused on performance, and they're using their replication capabilities to pull data from a remote cluster into the single connected high performance cluster where the AI engine is running or the model. How is this different than replicating within a single vendor storage system?
Well, because this presumes from the get-go that data is a distributed asset and will always be. So it's vendor neutral, it's storage infrastructure type neutral. Can use file, block, and object from any vendor in any cloud. You can run it in cloud instances or in VMs or on bare metal. So it can truly span all forms of infrastructure. And that having a data presentation layer and a data orchestration layer that can span everything, it really is the logical conclusion of, or the logical culmination of the march that file systems have been on since the dawn of computing. They started, inside the OS, local to only one server or, PC, put them on the network in an appliance. We made them scale out. We made them massive scale by dumbing them down into object storage. And now what we're seeing is that you can build a file system that's capable of simultaneously spanning all forms of storage infrastructure from all vendors. And what that does is it means that now data becomes something that is more concrete and real, because that data is something that exists independent of the infrastructure itself. So yeah, data orchestration is not just a new type of data management. Data orchestration represents a complete correction of the inverted upside-down relationship between data, a platform layer thing, and storage, an infrastructure layer thing.
So you challenge a lot of long-held thoughts in a lot of the architectures, and they're being adopted quickly. This idea of data permanence through orchestration, I think that's sometimes difficult for people to get their head around without really thinking on it. But you have a great example I've heard you use in the past about how smartphones and smart devices have accomplished this. Can you share that?
Sure, yeah. I mean, it happened without us even noticing it, and now it's become, we're so accustomed to it that we could never do without it. When you move from one phone to the next, when you buy a new phone, even if you abruptly lost your old phone, you don't even have to think about it anymore. All of your text messages, all of your emails, all of your photos and images, basically all of your personal content and data is orchestrated on your behalf by the iOS or Android ecosystem. And when you move between your phone and your laptop or tablet, you don't even have to think about it there either. Now all of your data is there on all of those. Data, consumer data, became an orchestrated thing in the past decade. And now it's indispensable. I mean, we can remember back to the days of shuttling floppy disks between PCs when you moved from one PC to the next, or between your laptops. Or we got more sophisticated and used thumb drives, and then we got more sophisticated and could hook up a network. Well, the ultimate level of sophistication is that the platform do it for you, because that data is simply orchestrated. And, consumer OSs have sort of done that for us. What we're talking about here is the foundational petabyte, even exabyte scale data that forms the foundation of very data intensive businesses, whether it's making movies or designing rockets or designing microchips, designing drugs. Data is at the heart of those, and that data, that unstructured data, which has now become a total goldmine with AI being able to make sense out of unstructured data. We don't have to go through the manual process of subsetting it to just the structured piece. Now that data needs to have the same transcendent existence to where it exists more permanent than any of the storage systems that hold it from one point in time to the next. And so our vision as a company is that, 5 years from now, people look back and say, how did we cope in a world where we had to manually copy things at huge scales of petabytes that would take months at a time, right? And you'd have to have your application down that whole time. How did we cope in a world like that? when with an alternative, the data simply exists in motion and is consumable while it's in motion, while it's granularly in motion. And that's what orchestration is it's the ability to present data, to consume it, even while it's in motion. And indeed make it so the data is, its inherent state is that it's always in motion. Right? I mean, just swipe a mouse and it can move from one system to the next, from one data center to the next, from one cloud to the next. It's on the presumption that data does need to be always in motion. Now, if it's sitting there for, at rest for a while because that works, that's great. But it's the default is the assumption that it's going to need to move. And this means getting rid of the whole concept of data migration. Data migration doesn't exist in a data orchestration world. Backups and restores don't exist. Those are just snapshots that are orchestrated onto different infrastructure in a self-contained way that you could reconstruct from. But in an orchestrated world, it's not a copy out onto some other thing like disk to disk or disk to tape. It's orchestrated behind the scenes, so it's all automated. There is no recovery from backup that you need to do. It's a snapshot, and the system knows how to refer to it if you need to recover that data.
So I think most people think of moving data around, whether it's a migration or a copy, as labor-intensive, time-consuming. How does Hammerspace make this concept of data anywhere, data in motion possible, and through some automation tools?
Well, that's where this becomes recursive, is that because we have built a data presentation layer capable of spanning all types of infrastructure in all locations and moved the data movement function behind that facade. So now you can be accessing and using data that is in motion. Now that you've done that, you can, for the first time, apply automation to deciding where to move the data, that proactive push and the reactive pull and learning from it. That's where this becomes recursive, because you can use AI and machine learning to make decisions about the physical distribution of the data onto the infrastructure. Now that it's not disruptive to move it, now that you can move it granularly, you can use AI and ML to be making the decisions about what data sets ought to be where, based on recognizing patterns or whatnot, with hints from those of us using it. And so it's kind of, to me, it's a cool thing to think one of the biggest challenges with AI ML workloads is getting the data sets to the systems where you need to do the training or the fine-tuning or the inference. And with a data orchestration environment, now you're able to use AI and ML to take over that, what was an extremely manual task, the data janitorial task of copy and merger and so forth. So we view this as using AI and ML to speed the cycle of using AI and ML.
Interesting. So I think that, as we wrap up, some of the pieces I've been hearing, unfortunately, I get the opportunity to work at Hammerspace as well. But as we think about between the funding, the market demand for data everywhere, with it, whether it's AI applications or as remote workers or as hybrid cloud environments, whatever it looks like, and then some really interesting customer adoption. You mentioned 300 to 400% growth and hyperscalers using Hammerspace for large language models. It's kind of the trifecta of massive opportunity for a company. And it must be a very exciting time for you as the founder to see everything that's going on.
It's very, we laid the groundwork. It's nice to see that that's coming to fruition, because the thesis was, if you can abstract data from the infrastructure and do it in a way where it unlocks performance, then if we look back at what VMware did with decoupling the OS and what's running on the server from the physical server, virtualizing the server, that came with a significant performance tax, but it was worth paying, because you got better utilization of servers that were sitting idle anyway, because you didn't have enough virtual server density on it. Well, we had this thesis that, look, using parallel file system architecture, we can make it standards-based and come out of the box and actually unlock parallel file system performance and abstract the data from the storage to make it orchestratable. And so it's like introducing virtualization without the virtualization overhead, but very much the opposite. Now you get unlocked parallel concurrent access to things where you didn't have them before. And that just opens up that spectrum from the challenges of data management at a global scale versus the challenges of feeding high performance data into, HPC clusters for doing AI and ML. And once you can put all of that under one umbrella, then it actually makes data orchestration something that can make sense, because now there's no reason to copy data out just to put it in something else where it can be served faster, right?
Yep.
And so it's really important that the file system be capable of addressing the full dynamic range, because then you can keep it within the same file system, within the same presentation layer, while moving it around. And so it's really great to see, because it has been a major investment. As you know, I started on this project quite a while back when I left Fusion.io. And we've had to move the standards body. We've had to build this into the Linux operating system to where it comes out of box. And it's just been laying these foundational building blocks piece by piece. And now we're starting to see that come to fruition. And some very large companies that recognize, what that means is I can use Linux as my storage nodes. I can use Linux as my client, all out of the box, and have a real file system, not an object store that I have to consume by rewriting my apps to use REST interfaces. And at the same time, I'm solving data orchestration and how to move data across different facilities. That is, I think, the trifecta for it, and we're glad to see it's got enough proof points with some very lighthouse accounts. I mean, when you have Jeff Bezos' own Blue Origin using Hammerspace as the data platform for designing rockets, but also for incorporating his own cloud, so it's their vehicle for hybrid cloud. That for me is just very exciting, and I can't talk about some of these hyperscale companies yet, but it's that order of magnitude impactful.
I think that is some great proof points. And for me, sitting in my chair, seeing a lot of the standards bodies rapidly reaching out to Hammerspace because of their enthusiasm, seeing what we're doing in Linux with the Linux or NFS kernel maintainer as our CTO, with contributions that actually stem all the way back to Fusion.io, but and some of the concepts you had envisioned back then. But seeing the mass storage conference, the IEEE, the OCP, all starting to express interest in integrating and leveraging these concepts, and Hammerspace's investment not just in their own technology but in making this standards base, I think is going to just fuel it as more wildfire than a proprietary technology that has to go it alone. So I think you've taken a great path. Definitely excited for the next session, whatever that episode is, when you come back to Data Unchained, and thank you for joining us.
My pleasure. Thank you.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.